In this video, we're going to quickly just review some volume material and also talk a little bit more about L'Hopital's rule. So first of all, find the area bounded between f of x and g of x. Well, of course, I'm going to set all these up just as integrals, and I'll rely on the fact that you could do that either in your calculator or by hand. The area, of course, is just the top function minus the bottom function. The interval here is from 0 to 2. 0 to 2. Top function is f of x, so we've got f of x minus g of x dx. Okay. All right, if we're going to revolve that around this line around y equals -3. So I don't have enough room to draw y equals -3, but it's something down here. So remembering that the function is going to give us the radius from the axis, we've made the radius 3 units bigger. So the big R would be f of x plus 3. Right, that'd be big R. Little r would be g of x plus 3. So we do big R squared minus little r squared, and we integrate it. Remember the pi out front. It's from 0 to 2. Okay, next, rotating around y equals -5, or I'm sorry, x equals 5, so that's over here. Well, rotating around a vertical line, we're going to need to rewrite our equations. So instead of y equals 2x, we're going to need to have x equals y over 2. And instead of y equals x squared, we're going to need to have x equals the square root of y. So the square root of y, of course, is here. This is y over 2. And the radius, because it's going to be rotated around like this, the radius is going to be the distance between 5 and the function. Well, the function every function tells you how far away from an axis you are. So I know that the total distance from the line to the axis is 5, and I want to subtract y over 2 to get the big radius. So we're going to have 5 minus y over 2 squared, that's my big radius, squared, and 5 minus the square root of y, that's my little radius, squared. So we're going to integrate that from 0 to 2, with the pi up front, and dy. And I could use one more set of parentheses. Last, R is the base of a solid where each rectangular cross-section perpendicular to the y-axis. Alright, so we're perpendicular to the y, so it looks like this. The rectangles are kind of coming off the screen at you. They look like that. So, of course, it's a rectangle. Got base and 3b. So the area is 3b squared. Well, to get the length of the base, I simply need to find the difference between the functions. The base is the square root of y minus y over 2. It just says how far apart those are. So I'm gonna bring the 3 out front, that multiplier. And I just noticed that my bound up here should have been 4. Apologize. The bound, because we're doing it with the y-axis, or dy, and the bounds are from 0 to 4, and that should be true of this one as well. Okay, so then we have the base squared like that. Okay, so again, let me just point out, because I made this mistake, this base should, or these bounds should be 0 to 4 because we're doing dy, and in terms of the y-axis, that's what defines those bounds define the shape. All right, last, if I wanted to put a vertical line so that the area bounded between those functions and the y-axis was 1/3 of r. Well, if you actually calculated the area of this, it was 4/3. Okay, r was 4/3. And I want to put a line in here somewhere. I'm going to call it at K. Okay, that cuts this to be 1/3 of r. So the red area should be a third of r. Well, r was 4/3. So a third of 4/3 is 4/9. So essentially, I want to set up an integral from 0 to k of my top function minus my bottom function such that I get an answer of 4/9. Well, the antiderivative would be x squared minus 1/3 x cubed, evaluated at k and 0. Plug in k, k squared minus 1/3 k cubed. I plug in 0, I get 0, and that needs to be 4/9. Well, you have some strategies to solving this, but I actually graphed it. I'm going to pull this in here. The blue is of course k squared minus 1/3 k cubed, and I graphed the line 4/9, and you can see the intersection point here. K needs to be 0.774. Now there are 3 intersection points, but remember the original area was found using the bound 0 to 2. So we were looking for the k value that was between 0 and 2. So this is where I would put a vertical line so that I would get a third of the original area. In this, let's just quickly talk about when we use L'Hopital's rule and what the limits are. This first one, if I plug in 0, I get 0 plus 0 over 0. So I can use L'Hopital's rule, and I'm going to do it kind of in a shorthand. Okay, just writing it right above it, finding the derivative. Now I plug in 0 again. So I get 4 plus 0 over 1. The limit is 4. This next one, I plug in 3, I get 9 plus 12 plus 1. That's 22 over 0. Well, 22 over 0, that's not one you can use L'Hopital's rule for, but this tells me that there's an asymptote there, so the limit does not exist. All right, let's do the next one, infinity. Well, as we go to infinity, remember we look at where the high power is. The highest power is on the top, so that means we're going towards infinity. Finally, we plug in 1, we get 1 minus 6 plus 5, so that's 0, over 0. So I'm going to use L'Hopital's rule. Derivative at the top, derivative at the bottom. I plug in 1, and I get negative 4. Please bear in mind that L'Hopital's rule, really you should rewrite it with a limit statement. For instance, saying the limit as x approaches 1 of 2x minus 6 over 1 equals negative 4. I'm just doing this in shorthand for the sake of time.